So welcome back. In the next section of MICES, we have two talks about Learn to Rank. And the first one is from Idealo, from Gennady, Shabanov, and Atakan Filgöz, about Idealo's journey on building production learning to rank system. Originally, it was started like two people, one of them joining remotely, but things never went good. So it's only Gennady. So the stage is yours.
Yeah, hi everyone. So we are two ML engineers, and besides us, we also have like 3 backend engineers, and we are responsible for search. And so we are ML engineers. We are responsible for making search better by a couple of percentage points with ML. So who of you knows about Idealo? Okay, so much people. So you already know probably how good our search is. So it's agenda, right? I will talk about a bit about of Idealo. So we define the problem, what kind of problem we solve with our learning to rank solution. We define solution, a bit of architecture, and we will talk about many about challenges, and we suggest also potential solutions for these challenges. And then at the end, I will give some general stats we have, the results we have. So we are Idealo. So the first part of the presentation, I will read slides because it's supposed to be presented by my colleague. So we are the fourth largest e-commerce website. We have 50,000 shops on our platform. We are in 6 countries, right? So we have 5 million products and 500 million offers. I will tell the difference later. What's that? What's products? What offers? And then we have 80 million visits per month and 18 million plus app downloads. So this is how usually our page looks like. So and we have this awesome query, iPhone 16 Pro Max. So this is usually how we test our search. If this query works well, then everything is good. I actually started 6 years ago. I tested with iPhone 10, right? But now, who cares about iPhone 10? I now test with iPhone 16. This is how the page looks like. And then if you click on the image on the product, so you will see the prices from different shops for this product. So this we already aggregated it for you, and at the top you have the cheapest price. So this is how our price comparison works. And actually we do it for 5 million products, and for 500 million products, you should do it by yourself on our platform. And so from the previous slide, right? So if you go to press some shop, like it redirects you directly to the shop. So we don't sell things. So talking about relevant signals, right? So we have relevant signal when person clicked on product and when he goes to some shop. That's for us only the relevant signal. So we don't have purchase data or add to cart signal. So that's important to know. So our search basically is based on Lucene. So we have on Lucene, and then at the top we have our custom solution. We have some mainly tuned boosting parameters, like so we boost. It's like they already like exist for 15 years. This boosting parameters. So you just say, okay, how much weights you put for when your query matches to the title, how many weights you put like when it matches to the description, and then we already have kind of ML. Like, right, when you use previous clicks, we put them in the index, right? This in some way, previous clicks for item for the given query. So this way we can boost our query, boost our products. And of course, like we want to go further, right? So we would like to use ML, of course. Then and what kind of problem we want to solve, right? So Usually we might show this result when you search for Apple TV. Why? Because like the products can be very noisy. And so they might have noisy description, and most probably this TV say, oh, like we have, you can connect Apple, I don't know, Apple TV, something to the fin, like, and then like we show them. And so, but at least we show one relevant result at the top, and people like click on it, and then we would like to learn from it, right? And if you understand, like if you have static ranking, right, so you can just know, okay, people click on that product. So it's hard to generalize, and then we want, let's say, generalize with the ML model. So we want to learn from this, okay, that if people, let's say, click on Apple TV, then probably they will search for Apple TV, like, and then we show them, re-rank them. And that's like how like the solution can look like. So you have some like searcher, there's some abstract word searcher, like we search, there is some backend which receives the requests, and then we ask Lucene for the results for the given query. We get the results, and then we request re-ranking, like re-rank for us some top 100 results, and then it's already here. We have ML solution, right? So, okay, then you decided, okay, to introduce like this component, learning to rank, and then you decide to build it from scratch, and then you open your Jupyter notebook, you import pandas SPD, and then what next? Like you should do something. First, right, you need to collect data because it's machine learning. You collect your data. So what kind of data you collect? Like you collect user interactions. Now in our case, we collect query item clicks. Then we collect product features we show to the user, and then specific thing like for learning to rank, it's query item features, like for example, how the query match to the product, for example, the score. And then like it's ML again, you might probably want to set labels based on your user interactions, based on our CTR. I hope everyone knows what is this. So click for rate. We set it to scale from 0 to 4, and then we should probably decide on offline metric. So it's in our case it's NDCG. Then we choose some simple features at the beginning, and then we start conducting experiments. And then when you come up with something smart and good, and you want maybe A/B test this, but before that, maybe you want to decide to update your model on the regular basis. So, or retrain, update features store. So you might want to build a pipeline, and then you run A/B test. And so this is the link for good reading. So if you start something, so it's from Google page, the rules of machine learning. So and then how this your data might look like. So you have query item features like text relevance and item position. Then you have item features like category price, and then you assign the relevance labels. We assign them based on CTR. The higher CTR it has, the higher relevance label it is. Okay, and you set up everything in the notebook, and you start running experiment. Of course, you want like to get better NDCG than your base ranking, right? Otherwise, what's the point, right? And the first problem we had, like, it was incredibly difficult to get NDCG better than your base ranking. And why it's the case? Because position bias problem. So the problem is that even if the product is not the most relevant, but if it's at the top, it still gets the most of the clicks. Then let's say you have some super relevant product for this query and it's on position 60, like it still has like a smaller amount of clicks. And then when you do your experiment, right, if you come up with some smart solution, and then your algorithm now pushes this item, the most relevant items at the top, but your NDCG evaluation will show, but you still have smaller NDCG because this most relevant item, according to your data, have less clicks than the one is in the top. So, and was the solution right? So we didn't try it yet, but we really have a high bet on like LLM labeling. So because it's unbiased completely, you just give the results and then give us labels. It doesn't care about position. Of course, you can evaluate and incorporate this bias, right? So you can, for example, check, okay, what's the CTR of the item when it's on the first position, what's the CTR of the item when it's on second position, and then you can incorporate this information in your algorithm. But it's at the beginning, it can be difficult because you should conduct additional experiments probably. The last thing, like you can just simply use during your training position feature, and then, but during the serving, you don't provide information about position. You just set the value 1 to all items. So that's, we recently found this ML rules from Google page. So we should definitely try it, but we didn't try. So the next challenge is the hidden bugs. Like if you compare with traditional software engineer, right? Usually, like if you have error, you have like exception, and you see this exception. And here you might have some mistakes, and you conduct experiments, and you can just get misleading results. And it's very dangerous because like it can lead to some wrong conclusions, and you can do some other things like trying to get more data, trying to change the model, but you just simply had a bug in your data. It's a lot of places where you can make a mistake. Like for us, it was really hard to get even evaluation done properly. Like even though like you have in DCG implement libraries with in DCG implementation, you can ask Gemini or ChatGPT to give your code, but there are a lot of tiny details that should be considered. For example, one of the problems I had personally, how to break the ties. For example, like let's assume your model predicts the same ranking score for all items. It just doesn't. It just dumb model, and then you have, of course, then you have like two items. One is the most relevant and has label 4. Another is least relevant, label 0. And then, like, of course, when you sort by this relevant score to calculate NDCG, the sorting doesn't change. So basically, your NDCG depends on the original order and data frame. And what I had the problem, like, of course, when you have your like table of data, and usually you sort by CTR to check, okay, what's the most relevant items for that query, and then you do experiment, and then you pass this data to your training model, and then you calculate NDCG, and it was always high. And then I was started reducing the feature, like to understand what's the problem. I just finally reduced to some dumb feature, and it still was high, and I couldn't understand that. And then I realized since it's already sorted by the most relevant item, right? When you calculate NDCG, it's the highest NDCG you can get, right, in your data, because the model predicts the same score for all items. There are many things I can talk if we have time, like data leakage. If you take, let's say, features from the future, let's say, so. We can talk later about this, and then the solution, right? So and test, and you should test, and then you should first of all understand the like why you apply this, and you cannot just simply throw your data into model and then just get some results and be happy. You should understand what exactly like this model learns. Okay, I forgot to mention by the way. So. Also, the suggestion here, like you don't need to try get better NDCG than your base ranking, actually, because of this problem of position bias. It's more important like that what kind of the features the model learned. It's more important rather than getting better NDCG than your base ranking, because finally the truth, A/B test will show the truth, right? So then you have like UI evaluation. So we have a UI evaluation to get like intuition behind the model. We just check, compare side by side, and we try to understand, okay, which item pushed up, which item pushed down, and then we try to understand why it's pushed down or pushed up, and then we have like this nice implementation of that chef values, like when you can select items on our UI, and then you can check, okay, why this item pushed up. So for example, here example, so like this popularity, it has a red color, so it has a high value. And for another item, the popularity has blue, so it has a low value of popularity. So it's the number of lead out basically from the the high value of lead outs popularity plays like positive impact, has a positive impact on the ranking. And like nice to see that, okay, price via price comparison platform, and we see that high price also influence negatively on the ranking, and low price it's so influenced positively. So it means that the model learns something meaningful. We're quite happy about this. Okay, then you decide to build pipeline to update your model on regular basis. And okay, the first challenge is incredibly takes a lot of time to build the model properly. Like especially if you're in the cloud, it's a lot of EAC code. It's a very error-prone approach. It may take up to several months. At least for us, it took several months to make it done properly. Maybe before A/B test, don't do this, right? Especially like if you, in our case, A/B test can take like 1 week. We can get meaningful results. So, and during the 1 week, it's not necessary to update your model. So you can just run like it is how you trained in your notebook. So you don't need to care. But anyway, if you build the pipeline, it's cool because you can run many experiments in parallel. So it's not the case when you have a notebook. It's not that easy anymore. Anyway, this is our pipeline. So we schedule everything with Airflow. We read the data with glue job in AWS, which is in PySpark. We create training data. We create feature store data. We have pre-processing step. Then we have cross-validation. And then finally, like, yeah, we want still to see that, of course, that like our NCG is better. Even it's not important, as I mentioned before, but it's like a safe check. If it's better, it's really cool. Then it's better. Then we create feature store. We have local feature store. We don't have through because of latency. And then we archive the model, deploy it, and then to endpoint, and then it's ready for A/B test. Then, okay, the next challenge, right? So you want to evaluate your model when it's already part of the whole search, right? When of the full search, because in the search you have some business rules, fallbacks, how it works as a part of the whole search. And we also, there are challenges, right? When you integrate a search in like re-ranking endpoint into search, then you pass already some features from production. It's not like that you use your notebook, you train on that on data frame, you train on that data frame, and then you use features from the data frame. So everything's static. Here is everything dynamic, like you pass the features around, like those engineers who integrate this, they might make mistake. For example, they pass prices 0 to you, and then it's hard to notice it because like it still re-ranks. And you might even notice that like its price is 0 because you see like still meaningful result, how it ranks. You check like top important features, and then it's still kind of, it just don't show this the price of the top features. You don't just see, so you should like debug. And then another solution we have, we just run one more time like NDCG evaluation over the whole search. So we just select already test variants, we pass test variant flags to our search endpoint, and then it triggers or not trigger the endpoint, re-ranking endpoint. Okay, then you started your A/B test. What challenges there is, then it's like you should already differentiate your clicks from which comes from your base ranking and the clicks which comes from your model. And especially if you want to retrain your model during the A/B test, and if you want to update feature store for you. So you already cannot use your clicks from base ranking, because this is what you will not have in production, right? When you deploy in production your model, it doesn't have anymore the clicks which will be produced by base ranking. So for us, it was difficult to differentiate, right? So, and what's the solution, right? Probably you can investigate this kind of data leakage impact, how it impacts you during A/B test, or like our solution, we just don't retrain and don't update the model during A/B test to have a clean experiment. Okay, then you deployed your model in production. How to retrain this? The problem here right now, your model produced the clicks, right? And now the clicks bias toward your model. And then if you like model has some biases, and it will have biases, you basically, if you retrain on its own output, you will have real problems, because these biases will be amplified. And then that's what we basically observed. Like we just after some time, at the beginning we just retrain every day the model. Why not? Like what we observed, like first of all, from visual perspective, the quality degraded significantly, and we started investigating why. And then this is the plot which indicates the feature importance, how it's changed for feature importance for the model. And then this is the red line is when it's end of A/B test, basically time when we deployed. And then like this text relevance importance drops significantly. And then the previous item, previous query item CTR increased significantly. What it means that basically a model starts relying on its own like clicks, right? So we say, oh, the clicks I predict are the most relevant feature, and then just visually it was obvious that it was bad. Again, like solution, if you kind of manage to set up LLM labeling, like we believe it's unbiased. So even believe that it will solve our problems. Another solution, you can implement exploration traffic. So you don't touch some traffic at all by your ranking algorithms, and then you use this traffic for evaluation and maybe even retraining. And then, yeah, again, applying correction bias, apply bias correction. Okay, what to monitor? It's the most difficult part for us, and we still don't have proper monitoring. So of course you have technical metrics like latency, all these things, but the quality, right? If you disable your re-ranking model at all, right, will someone notice it, right? I would say the answer is no. No one will notice it, because like if it usually it gives like at the beginning you a couple of percentage points of improvement. Like if you disable, who will notice it? So, and that creates the difficulty. If you even like we suggest like to check something simple like CTR, overall CTR per query, but like if it's changed by 2%, right? So down on the, you just not notice because it's oscillate like every day. So the only suggestion we can give here, like if you start tracking, if you still continue tracking the difference between your base ranking and your the model, so then it doesn't make sense anymore when you model in production, because the difference will grow because already clicks are biased toward your model, but it just doesn't tell anything. So we had a huge gap between the base ranking and our model over time. And finally, we realized that just model doesn't perform well just from visual perspective. And of course, the last but not least, but latency, you want to be fast because it's kind of, you introduce additional component, right? You have your main search latency, and then you kind of additionally request your ranking endpoint to re-rank results. And then it's like you probably want it within like 40, 50 milliseconds. Right, here a suggestion, right? Use, of course, everywhere vectorized version of Python, like especially for pre-processing logic, because it takes maybe most of the time pre-processing of the feature. And then would really help us to reduce time significantly by 10 or 20 milliseconds per request, which is a lot. Like we use like some hint from LightGBM library. We use LightGBM that you treat categorical variable as a number, not as a categorical variable. And if this category has high cardinality, then it's okay, but it saves a lot of time for you. So for example, like categorical value is category of the product, right? It has 2K different categories we have. So it helps us. So of course, the solution, right? Like benchmark tests, load tests when you deploy in production, so on. This is the overall statistic we have. Like we have really actually simple model. We apply it to the whole catalog. Like I think every second request at Idealo is served by the model, even more maybe. Like, and then we rank top 200 results from which we get from Lucene. The whole pipeline just runs within 1.5 hours. Like we have 46 features. For the training, we use 5.5 million query item pairs. Yeah, we use lambda rank from LightGBM. And then our average response time is 40 milliseconds. And then its average request per second is 60. It was more before, like, but then we changed a bit our logic. So it's less now a bit. So this is our A/B test results. So we improved like, so for half of our traffic, you can say, right? So consolidated conversion rate by 1.37, then ratio of sessions exiting after the search, when user search, then he exits like -2%, -2.3, and then exit rate -1.63. That's it. Thank you very much.
So, questions?
Thank you for the talk. It seems very challenging to be on a marketplace where you cannot observe the outputs. It seems very challenging to be building a marketplace, but you cannot see people buying. You can only see them going to another shop and maybe buying, maybe not. So I guess that brings some bias, because maybe a product looks super good. I'm going to click, but then I get on the website and there's like little lines that make me not buy.
We don't know.
So do you see ways, I mean, this is very machine learning focused, but do you see ways where you can also get that signal back from those places? Do you think it's a possibility that by integrating deeper into the platforms, the Shopify, etc., you could get that data? Or do you think you have to do without it anyway?
Like we have some data which say earnings from the shop. It's difficult. Let's say, I think Amazon or eBay, they don't even say for each item the earnings came. They just distribute equally across all the items on the which came, so on their platform. So it's for some shops you can do this, but it's really challenging, and it's not even our job. But we tried basically to train on first on clicks, then we tried on lead outs to the shop, and then we tried to on the earnings. It was simple, just changing a bit ETL and then running. And the problem was when you train on lead outs or even earnings, which we didn't know that they're wrong at the beginning. So we started pushing offers up. Why? Offer is like, as I mentioned before, it's like it's not a product, it's offer. It's basically listing. When user clicks, he immediately redirected to the shop. And then with the product, you first click on the product, and then you redirect, and then you can like click on the shop, right? And then the model started pushing up like offers because they have better ratio of lead outs, right? So because you just need one click instead of 2 clicks to produce lead out, and then it's caused like problems. At the beginning, just okay, let's go with clicks. But I'm pretty sure there are some solutions to work around this.
Super interesting. Thank you.
Thank you.
Yeah, thank you for the very nice talk. I was wondering, like, you seem to have quite a bit of confidence that like LLM-based labeling would solve quite a bit of things, and it's plausible given position bias and stuff like this. But there's also a lot of doubts connected to this, right? Why should this be completely unbiased? So did you ever try to like select a sample set of queries that you then just say, okay, I asked the LLM what the perfect ranking would be, and then I just shoot this live for a few selected ones to quickly test the hypothesis that you're making?
You mean that we kind of label or rank with LLM, and then we basically, for these ranked items, we just run A/B test and check if it makes sense, right? That's the question.
Yeah.
Well, we have like 500 million, right, products, and I'm just okay. We will rank, I don't know, 1 million. Say okay, it's awesome. Ranking is awesome, but then it will show us for these products. It will show us good results. But the next thing, right? So you should use this data to train, like, I guess, learn to rank model, right?
Yeah, sure. Like as soon as you know that this is kind of
you
valid.
mean if you like to reduce the, you mean that to make sure that okay, the LLM labels perfect, right? So yeah, we can do this. It will be next step, but first step we just try it simply, just label it for us to see, because usually we check visually first, right, to learn intuition, and they didn't show like at the beginning good results. So it sounded like we need some time to think about prompts, how we should apply prompts to label how we want. Yeah, but definitely it's the next step, right? it's but a good suggestion. Thank you.
Yes, I'm too far away. Sorry.
I have a question about using clicks to train the model. When we do qualitative research about search relevance, what we see is when some people define search relevance not just by the product, but basically the overall search results. For example, when you search for a vacuum cleaner, they want to see brand variety. Or eventually they don't define, like relevancy is not just defined by the clicks, but also the items you don't click define the relevancy. How would you capture it while training this model? Because this is definitely a straightforward approach, and click itself is like quite confident, but I'm also thinking about the items you don't click. They also make the search relevant in a way. How would you handle this?
Yeah, as you mentioned, right, it's not straightforward anymore, right? Clicks are straightforward, and like presentation was about when you start from scratch, of course, you want straightforward solution. The next step, right, so even from your definition, right, you say when people don't click on it, it's relevant. Okay, but then I should somehow figure out how it's relevant. We don't know yet. So of course, like people can, I don't know, click some filters, they click something else, like on the page, but still it doesn't tell us obviously what is relevant or not. We have some post-processing logic, which basically make results diverse from different shops. Okay, maybe you can measure, I don't know, how the most relevant item is similar to the item which is not clicked at all. Or you can even, let's say, randomly shuffle periodically. That's what I was talking about, this evaluation of position bias. Basically, this is part of evaluation of position bias when you, let's say, there is some item which has 0 clicks, but it can be relevant because it's just at the bottom, right? And then you maybe want randomly shuffle it at the top and see what's the CTR of that item. But as I mentioned before, so then it requires additional efforts, right? So it requires additional experiments to do this, right? But usually, if you decide to start your learning to rank project, you don't have this data. So, but you won't just right now deliver model. So that's.
So, time for the last question.
Okay, I wanted to ask a question about the explicit label. What was the main reason you decided to bucketize the CTR and not train a model directly on implicit queries?
You mean directly on CTR, right? Or
yeah.
It's because like the most popular is lambda mart from solution, right? And then like it's just requires from 0 to 31 label. To my knowledge, right, from LGBM library. And then we found a paper from Walmart, which basically they do the same, they convert CTR to labels, and then that was kind of.
Yeah, I'm just thinking if you, so then did you present the query with all the pairs, or did you sample according to what the user saw? So let's say the query has been searched 500 times, but you have aggregated all the labels and then only trained on the aggregations, not the multiplication of.
Yeah, we train off aggregation and we assign weights to the samples. Like,
okay.
Yeah. Yep. So number of impression is the weight, basically, I think. So.
Thank you. I will probably ask you about the paper. I'm interested in this. Yeah. Thank you.
So thank you very much. Let's close.